In this section, we're going to take a look at trig integration. So we're going to do integration with trig functions. We're going to take a look at a couple of techniques. Some of those are going to match up with the substitution stuff we did a couple of sections ago, and some of that stuff will be new, utilizing some trig identities. So let's start out with substitution. So basically, we can do a substitution where we substitute out our trig functions. In other words, we're going to let our u substitution equal a trig function. So we're going to do that substitution, and then we're going to take advantage of two other issues as well. One of the issues that we're going to look at is some trig identities. So when I do this substitution, I'm going to utilize some trig identities to be able to algebraically rewrite my problem so that it makes it easier to do. Now, whenever we substitute out a trig function, whenever we substitute out any function, we need to make sure that we get the correct differential exchange. So we need to do the du that matches up. And that differential exchange will be essential when thinking about what trig function to originally use. So when we're thinking of what do I let my u be, which trig function I let my u be, the differential exchange at the end is going to be important. So let's do an example here. We have sine of x times cosine to the fifth integrated with respect to x. So there's a number of things I could do here. I could try to let u be sine. I could also let u be cosine. I could try to let u be cosine to the fifth, but it turns out the best u to use here is setting u equal to cosine. It's kind of like the inside function there. This is a cosine raised to the fifth power. Now, when we take a derivative with respect to u, or excuse me, with respect to x, the derivative of cosine is negative sine. So we get negative sine x is equal to the derivative of u with respect to x. That means our differential exchange is going to be du is negative sine of x times dx. So now I'm ready to rewrite my original integral and do my substitution. Actually, you know what I will do? Instead, since we have a sine x dx and they're positive, I'm going to move my negative over to the other side and say, well, sine x dx is equal to negative du, instead of saying du is equal to negative sine x dx. So this sine of x will kind of put back next to the dx. Then we do our u substitution. And cosine is being raised to the fifth power. So that is a u to the fifth. And the sine x dx becomes a negative du. Now, the way I'm going to write this, I'll put the negative in front of u to the fifth. Now I'm ready to integrate. So I integrate. Antiderivative of negative u to the fifth is negative 1/6 u to the sixth plus c. And remember, u was cosine of x. So my final answer would be that this integration winds up being negative 1/6 times cosine raised to the 6th power, obviously plus c. Now, this is not the only way I could have approached this problem, but this is the cleanest, most efficient way. And basically, when I let my u be cosine, I could find a differential exchange that paired sine of x with the dx. And that led to this process. Now, this process, as you see it in this example, is very, very similar. In fact, it's the exact same thing as the substitution that we looked at in section 6.1, or in one of the previous sections, in the substitution section of this course. But we'll deal with why the trig integration is its own thing, is because we'll deal with some other applications or other ways of going about this in just a moment. Let's take a look at example 2. Example 2 wants me to integrate tangent by using substitution. Basically, this trig, substituting out a trig function for my u. Now, when we look at this, this is one that we passed over in the previous section. In the integration by parts, this came up, an integration of how to integrate tangent. So we're going to show how this is done here. Now, the first thing to realize, the first tool that we're going to use here is the fact that tangent is equal to sine divided by cosine. So we're going to integrate sine of x over cosine of x, obviously with respect to x. So basically I used a trig identity, the trig identity of what is tangent, in order to rewrite the problem. So I use that trig identity, tangent is sine over cosine, and then I'm going to let u here, well, I'm getting sine or cosine to be u. And in the previous problem, we saw that it's nice that if u is cosine, then sine can pair up with the dx. So I could pull out a sine and pair that up with the dx. So I'm going to let u be cosine of x. And just as in the previous problem, the derivative of u with respect to x is negative sine of x. So my differential exchange I could write as du is equal to negative sine of x times dx, or I could move the negative on the other side, which is what I'm going to do. Negative du is equal to sine of x dx. Now I'm ready to do the substitution. So I'm going to rewrite this as an integration of, I'll put 1 over cosine of x times sine of x dx. So I'll basically just factor out the sine, pair it up with the dx. And now notice what happens. When I do my u substitution, this is the integration. 1 over cosine is going to give me 1 over u. And then sine x dx gives me a negative du. I'll put the negative in front of everything, and there you go. Now, what's the antiderivative of negative 1 over u? Well, the class of antiderivatives is natural log of u. And then I got to put a negative out front. So negative natural log of u plus c. But remembering remembering what u was, that tells me that this is negative natural log of the cosine of x. And as always, plus c. So that's what integrating tangent gives you. So when I integrate tangent, I get negative natural log of cosine of x plus c. Interestingly enough. So that's the antiderivative of tangent, negative natural log of cosine. You can do a similar thing with cotangent. You can do a similar thing with some other things as well, but that's my final answer is negative natural log of cosine plus c. Let's take a look at example 3. We want to integrate this using substitution. Now, if I let u be secant, then the derivative of secant is secant times tangent. If I let u be tangent, then the derivative of tangent is secant squared. Since I already have a secant squared, that's what I'll probably do with my u. I'll probably let u be tangent, and then the du will involve some secant squared. That's probably the safest option, although you may be able to do some other things as well. So probably my easiest option is going to let u be equal to tangent of x. I know both of these are raised to exponents, but if I let u be equal to tangent of x, then the derivative of u, obviously with respect to x, is going to be secant squared of x. And I already have a secant squared of x in my integration. So when we multiply, or when we do our differential exchanges, let me say that, when we do our differential exchange, du can replace secant squared of x dx. So there we go. And now I'm ready to do my substitution. Again, I'm going to rewrite this. I'm going to put the secant squared in the back next to the dx, just so that visually speaking, I can say, oh yeah, this one is the one that's my u, and, or excuse me, this one is the one that is my du, my differential exchange, and tangent to the fifth, that's going to be u to the fifth. So we get u to the fifth, secant squared dx just becomes a du, and now I can integrate. So since we're integrating with respect to u, we get 1/6 u to the sixth plus c. And then since u is tangent, my final answer is equal to 1/6 times tangent to the sixth of x plus c. So That would be my final answer when I integrate tangent to the fifth times secant squared. Let's not highlight that. Undo. Good. So hopefully those are straightforward processes. Now, oftentimes it gets tricky on what to call your U or what to call your U. And that's where we really have to kind of focus on this differential exchange. In this case, letting U be tangent allowed for this differential exchange. It turns out that if I let U be secant, it would have also worked, but I would have had to use some other tools. That's not always the case, though. Sometimes certain U's work and other U's don't. So sometimes they both work, sometimes one or the other works, and sometimes neither works to give me a good differential exchange. So let's do one more example of this type of problem. And I'll have you try to integrate sine times cosine using substitution. You can push pause on the video and try that on your own if you'd like. Now, I'm going to do this problem in two ways. So I'm going to do it right now, but I'm going to do it in two different ways to lead us into the next thing. So basically, the first way I'm going to do this is I'm going to let u be equal to sine of x. If I do that, then the derivative of u with respect to x, the du dx, is equal to cosine of x. That means my differential exchange is du is equal to cosine of x times dx. Again, that looks like multiplying both sides by dx, but it's a little bit trickier than that actually algebraically. But if you think about multiplying both sides by dx, turns out it always does the same thing. Even though this is an operation, not a fraction. So anyway, what that means is that this integration can be written as equal to, well, sine is my u, so that's going to be u. Cosine of x dx is my du, so that's just u times du. When I integrate u to the first power, I get 1/2 u squared plus a constant. U here is sine, so I get 1/2 times sine squared of x plus any constant that I want. So that would be my final answer. Or at least that's one version of my final answer. Let's do this another way, and I'll come back to this one. So let me start a new page there. Let's say instead of letting u be sine, what if we let u be cosine? Then the derivative of cosine, derivative of u with respect to x, is going to be negative sine of x. So my differential exchange is going to be du is equal to negative sine of x dx. Or, in other words, I could put the negative on the other side, which is what I'm going to do, and say negative du is equal to sine x dx. So when I put the sine next to the dx, I'll go ahead and rewrite that. We see this a little bit better. Cosine is my u. The sine x dx is negative du. Let me put the negative out front. And so when I integrate, I get negative 1/2 u squared plus a constant. Now remember, in this case, u is equal to cosine. So this is negative 1/2 cosine squared of x plus c. So I did it the first way, and I got a positive 1/2 sine squared plus c. I did it this second way, and I got a negative 1/2 cosine squared plus c. And we may ask, well, which one is right? Which one is wrong? And it turns out that they're both right. These two expressions are actually equal. The reason that they're equal is that there is this trig identity that says cosine squared of x plus sine squared of x is equal to 1. And therefore, if I took this thing and if I replace the cosine squared, so let me copy that. If I replace the cosine squared with 1 minus sine squared, because if you solved for cosine squared, you get 1 minus sine squared. Oh, let me rewrite this. So if I replace the cosine squared with 1 minus sine squared of x, and then I multiplied through, what we would get is negative 1/2 times 1, that's negative 1/2, plus sine squared of x plus a c, but negative 1/2 plus a constant is, or excuse me, I mistyped there. Negative 1/2, this first numerical value, plus a constant is the same thing as just any other constant, some other different constant, so that 1/2s can be absorbed into the constant. All right, not the coefficient of 1/2, but the constant of 1/2 out front. So because of trig identities, these two are actually equal. So that shows you that oftentimes there's a couple of different ways to integrate. You can do either. In this case, I like to use u as sine. So in this case, you could have done either, but they're going to be algebraically identical because of the trig identities that we have. Now, this brings me to the next part of this section. So far, we've just done u is equal to a single trig function, and then our differential exchange was something else. We used the tangent identity on this example too, but we hadn't used any other identities. Well, when we have cosine and sine to higher powers, or if we have secant and tangent to higher exponents, or cosecant and cotangent to higher exponents, then we can also add these identities to our tools of manipulating the integration. In particular, we're going to use the Pythagorean identities a lot. Now, the Pythagorean identity, the main one, deals with the unit circle. And if you remember on the unit circle, cosine of an angle and sine of an angle give you a point on the unit circle. So therefore, cosine squared plus sine squared is equal to 1. This is known as the Pythagorean identity for cosine and sine. If you divide each of these three terms by cosine squared over cosine squared is 1. Sine squared over cosine squared is tangent squared. And 1 over cosine squared is secant squared. So dividing this Pythagorean identity by cosine squared gives you another Pythagorean identity involving secants and tangents. And then if I took my original Pythagorean identity and divided by sine squared, cosine squared divided by sine squared would give me cotangent squared. Sine squared divided by sine squared gives me 1. And 1 over sine squared gives me cosecant. So this gives me 3 Pythagorean identities that all come from the single Pythagorean identity. So we can manipulate using these identities to rewrite a trig expression into one that's easier to integrate. Let's do an example here. We're going to integrate by substitution and using some identities, in particular, these Pythagorean identities. Now, it's really nice that with those Pythagorean identities, cosine and sine are paired, tangent and secant are paired, and cotangent and cosecant are paired because the derivatives of sine and cosine are linked. The derivatives of secants and tangents are linked, and the derivatives of cosecants and cotangents are linked. So let's do this example along with utilizing one of the Pythagorean identities. Okay, so here's what we're going to do. Now, I know how this is going to end up, but I want to show you what sort of thinking process you could be using here. The first thing I need to do is decide what my u is going to be. And in order to decide that, I really need the right du. I need the right differential exchange. So you don't write this down right now, but if you used u as equal to sine of x, then du would have been cosine of x dx because the derivative of sine is cosine. That would make the integration u to the third. Well, let's rewrite this. I would have to pull off one copy of cosine and sort of tack it on with the dx. So I'd get sine to the third. I'd get one copy of cosine all alone. And then I'd have to pull off a copy of cosine and pair it with the dx. So this would be my du. I would have a u to the third. And then I'd have this extra cosine sort of all alone by itself. And then I get stuck. I get stuck with an extra cosine that I can't deal with. So this approach where I let u be sine and my du becomes cosine times dx, this approach is not going to work. So I go back up and I say, well, let's switch it up then. What if I let my u be cosine? The derivative would be negative sine. So I'm going to say negative du would be equal to sine of dx. This is the correct way. So let me do all of the steps here. Derivative with respect to x is equal to negative sine of x. And then negative du is equal to sine x dx. So if I did that, then for my differential exchange, I could pull out one copy of sine and put it next to the dx. So I would end up with a sine squared times cosine squared times a sine of x dx. Now the sine x dx is going to work really nicely with my differential exchange. This cosine squared, that's just going to be u squared. But now I have to deal with a sine squared. However, this is an even power. So I can go back to my Pythagorean identity and my Pythagorean identity says that cosine squared plus sine squared is equal to 1. That means I can replace this sine squared with a 1 minus cosine squared. And so watch what happens when I do that. When I take this integration, I have to rewrite it. So when I take this integration and I take out the sine squared and I replace it with 1 minus cosine squared, now all of a sudden, apart from my differential exchange where I need a sine, everything else is written in terms of cosines. So I can do a substitution with my u and my du right now. I'm going to take 1 minus cosine squared, that's 1 minus u squared, times cosine squared, that's another u squared, times sine x dx. Now that's going to be negative du. I'll put the negative out front. This thing is pretty easy to multiply out and integrate. So let's multiply that out. We'd get negative, so the negative times 1 times u squared. So this is basically like negative u squared times 1, so you get negative u squared. When I take negative u squared times another negative u squared, negative times negative gives me a positive, u squared times u squared gives me u to the 4th. I should probably adopt some good notation there. So I get negative u squared plus u to the 4th when I multiply it out. And those are two terms that are easily integrated with respect to u. So I simply integrate those with respect to u. I get negative 1/3 u to the 3rd plus 1/5 u to the 5th plus c, which, since u was equal to cosine, that is negative 1/3 times cosine to the 3rd plus 1/5 times cosine to the 5th of x plus c. And that's my final answer. So if I am trying to find the integration of sine to the 3rd times cosine squared with respect to x, my final answer is negative 1/3 cosine to the 3rd of x plus 1/5 cosine to the 5th of x. And if you do take a derivative, it won't immediately look like this, but it will be algebraically equivalent to this. So that's what we end up with. Now, the key thing here was seeing that in order to make u cosine, I needed to pull off a single copy of sine, and that left me with an even power of sines, which I can use my Pythagorean identity to. But if I'd have tried that the other way, if I'd have tried to let u be sine, then I'd have to pull out one copy of cosine to match with the dx for the differential exchange, and that would give me a cosine to the 1st power remaining, which doesn't work nicely with the Pythagorean identity. So after I pull out my thing I'm going to use for my differential exchange, I want even powers in order to use these Pythagorean identities. So that was the key there, letting u be cosine, and then everything works out nicely. Let's take a look at the next example. We want to integrate by substitution and by using the identities. We're going to do sine raised to the 7th power of x and times cosine raised to the 3rd power of x. We're going to integrate that with respect to x. Now, in this case, it turns out you can let u be equal to sine, and you can let u be equal to cosine, but because there's a higher power on sine, it's actually going to be a little bit easier to use sine as my u as opposed to cosine. So let's go ahead and do that. So u is going to be equal to sine of x. I'm going to start out doing this. That means the derivative of u with respect to x is going to be equal to cosine of x. And that means the du is equal to cosine of x times dx. So that's my differential exchange. So what I'm going to do is I'm going to take that integration and I'm going to start out by rewriting it. I'm going to pull off one copy of cosine and stick it next to the dx so that I know that's my differential exchange. U being sine of x, that is going to take care of this part. That's going to be u to the 7th. And then I have this cosine of squared. Well, the cosine squared can be replaced. Didn't put the equal sign there, but the cosine squared can be replaced using that Pythagorean identity. Just like here, we can replace it with 1 minus sine squared. So cosine squared can be replaced with 1 minus sine squared. And now we're off to the races. Now we're ready to integrate, or excuse me, now we're ready to substitute, and it'll be easier to integrate then. So sine to the 7th is u to the 7th power. 1 minus sine squared is 1 minus u squared. And then cosine x dx, that all turns into a du. So that's what we end up with. The next step is multiplying the u to the 7th times both terms inside the parentheses there. This gives us u to the 7th minus u to the 9th. We integrate that with respect to u. When I integrate that with respect to u, I get 1/8 u to the 8th minus 1/10 u to the 10th plus c. U in this case is sine of x. So that is 1/8 sine to the 8th of x minus 1/10 sine to the 10th power of x. Plus c. That is my final answer. 1/8 sine to the 8th of x minus 1/10 sine to the 10th of x. That all came from letting u be sine of x in this problem. Now, I do want to state you could have done this using u as cosine of x in this case as well. If you did that, I'll kind of skip some steps. You don't have to write this down or anything if you don't want, but if you did that, derivative of cosine is negative sine. And then when I do my differential exchange, we get negative du is equal to sine x dx. I could have, therefore, pulled off one copy of sine and paired it with the dx. And then using my Pythagorean identity, sine squared is 1 minus, which means, 1 minus cosine squared. What's sine to the 6th? Well, sine to the 6th is the same thing as sine squared raised to the 3rd power, right? Anything to the 6th power is like squared raised to the 3rd power. And if I think of my problem like this, since sine squared is 1 minus cosine squared, I could have done my exchange this way. I would have had 1 minus u squared raised to the 3rd power times u to the 3rd power times du. Actually, times a negative du, excuse me. Put the negative out front there. Notice, however, this would require us to take a polynomial to a 3rd power, which is quite a bit of algebraic work. And so This one would be a little bit more algebraic work at this step. It's still doable. It just takes more algebra. Okay. I'm not going to do it this way because if you did do it that way, you'd get your final answer in terms of cosines, and that final answer in terms of cosines would be equivalent to this final answer in terms of sines. So like I said, I'm not going to do that um, by hand, but you can kind of see where this is headed. So you could have used either, but utilizing u equals sine of x, because sine is raised to the higher power, that one was a little bit of a better option in this case. We've done a couple of examples with cosine and sine. So now let's do an example with secant and tangent. Example 7 wants us to integrate secant to the fourth times tangent squared. What I like to do when I'm deciding these is I like to give myself both options to begin with. If I let u be secant, or if I let u be tangent. Those are my two options. If I let u be secant, then when I take a derivative of secant, I get secant times tangent. If I let my u be tangent, sorry, du dx. So that's what happens if I let my u be secant. If I let my u be tangent, then the derivative of u with respect to x is equal to secant squared. So I asked myself, which one of these is the better option? If I let my u be tangent, then this will be u squared. I'll have a secant squared that I need to pull out with the dx, and I'll be left with a secant to the second power. So if I let my u be tangent, it seems like that's going to work. On the other hand, if I let my u be secant, I'll have u to the fourth. I'll have tangent. Well, I can pull out a secant and a tangent, pull out one copy of secant from here, one copy of tangent from here, but that'll leave me with a tangent to the first power. I don't like tangent to the first power. I like tangent to the second power with my Pythagorean identity. I like secant to the second power with my Pythagorean identity. So what I'm going to do is I'm going to use tangent as my u, because that leaves me with even exponents on secants and tangents. Hopefully that makes sense. You can go through the whole process if you'd like. If you start down one path and you mess it up, don't worry too much, because you can always go back and restart with the other. But it turns out this is the path that is going to yield the best results. So my differential exchange is that derivative of u is equal to secant squared of x times dx. I'll rewrite this in two different steps. So the first thing is, since I have a secant squared dx, I pull out secant squared and I put it next to the dx. And I say this is going to be the du when I do my differential exchange. Here, u is tangent, so u squared is going to be fine here. But secant squared I have to deal with. So I'm going to replace my secant squared with the appropriate thing from the Pythagorean identity. Now remember, we get the one with secants and tangents by dividing both sides by cosine squared. So 1 plus tangent squared of x is equal to secant squared of x. So notice that secant squared is going to be 1 plus tangent squared. Be careful on this because the way secants and tangents interact is not the same way as the way cosines and sines interact. So secant squared can be replaced with 1 plus tangent squared. So that's what I'm going to do. I'm going to take this secant squared. I'm going to replace it with 1 plus tangent squared of x. And now I'm ready to substitute. So now I do my substitution. 1 plus u squared times u squared times du, which means I'm going to be integrating 1 plus u squared times u squared with respect to u. When I distribute that u squared, I get u squared plus u to the fourth. That's what I'm integrating with respect to u. Which means my answer is going to be 1/3 u to the third plus 1/5 u to the fifth plus a constant. And those u's get replaced with tangents because that's what the u was. So 1/3 tangent to the third of x plus 1/5 times tangent to the fifth of x plus c. That's my final answer. And again, in this problem, it would have only turned out this way. Tangent would have worked, but if I'd have used u is equal to secant, it would not have worked. So that's my final answer. Let's do another example. This is example 8. It says to integrate secant to the third of x times tangent to the third of x with respect to x. Okay, so this one I have to think again, differential exchange. In this case, if I try to let u be equal to tangent, then the derivative is secant squared. When I pull out a secant squared and pair it with the dx, I'm left with secant to the first. So in this case, letting u be equal to tangent is not going to work. Therefore, I should try u is equal to secant. And when I let u be equal to secant, then a good thing happens. The derivative of secant is secant times tangent. And so my differential exchange is going to be secant of x times tangent of x times dx is equal to du. So that's the differential exchange that I want to use. So that means that's the u that I want to use. Let me give one space there. So the first thing I do is I pull out a secant tangent and pair it with the dx. That's going to lower the exponent on the secant and lower the exponent on the tangent, each by 1. Now u here is equal to secant, so I need to get rid of this tangent squared with a secant. Tangent squared, if I subtract 1 from both sides, tangent squared can be replaced with secant squared minus 1. Again, that's just using my Pythagorean identity and solving for tangent squared. So secant squared minus 1 is equal to tangent squared. So that's what I do. I replace the tangent squared with secant squared of x minus 1. And now I'm fit to do my substitution. Secant squared becomes u squared. Secant squared minus 1 becomes u squared minus 1. And then the secant times tangent times dx, all of that becomes my du. Multiply, you'd get u to the 4th minus u squared integrated with respect to u. Let me rewrite that just a touch bit nicer. When we integrate that, we would get 1/5 u to the 5th minus 1/3 u to the 3rd plus some arbitrary constant. U here, remember, is secant. We started with u as secant. And so we get 1/5 secant to the 5th power minus 1/3 secant, whoops, to the 3rd power plus whatever constant we want to tack on at the end. So that's how we integrate these integrals involving secants and tangents. Now, in the previous example, it only worked when u was equal to tangent. In this example, it only works when u is equal to secant. There are examples where it works either way. And there are examples in which maybe the u equals secant and u equals tangent, neither of those options work, and we need something else. If I ask you to integrate using identities with secants and tangents, it'll work out one way or the other. You can either let u be tangent or u be secant. One of those options is going to work, and maybe both of them. Let's do one more using the Pythagorean identities, but this one we haven't dealt with so far. We haven't dealt with one that involves cotangents and cosecants. So we'll deal with one that involves cotangents and cosecants here. Now this is cotangent cubed times cosecant cubed, so it's going to work in a very, very similar way as our last problem. We had both raised to the 3rd power. And secants and tangents in general work in a similar manner to cotangents and cosecants with our Pythagorean identities. It turns out in this case that I'm not going to go through the option that doesn't work. I'm just going to give you the option that does work. So the option that does work is letting cosecant of x be our u. Now, if I take a derivative of cosecant, I actually get the negative of cosecant of x times cotangent of x. So I get this extra negative symbol. And so my differential exchange will be that cosecant of x times cotangent of x times dx is the negative du. I'm going to do my normal thing. I'm going to pull out one copy of cosecant, one copy of cotangent, and put it next to the dx. So that'll lower these exponents by 1. So that cosecant, cotangent dx, that'll become my du. The cosecant squared, that'll become u squared. And now I have to deal with the cotangent squared. I deal with that using the Pythagorean identity. And I've actually written that down. If I take my cosine squared plus sine squared equals 1, divide by sine squared on both sides, I get that cotangent squared plus 1 is equal to cosecant squared, which also means that cotangent squared is equal to cosecant squared minus 1. So that's what I'm going to plug in. I'm going to take that integral and replace the cotangent squared with a cosecant squared of x, obviously, minus 1. Now I'm ready for my substitution step. We go u squared minus 1 multiplied times u squared, and then again cosecant, cotangent dx, that all becomes my du. When I multiply through, oh, I'm sorry. I misspoke there. Cosecant times cotangent times dx does not become du. It becomes negative du. So I gotta put in my negative symbol. I think I'm going to put it in right here in front of the u squared. That might be an easier way to see it. So forgot to put in my negative du. Doesn't become du, it becomes negative du. So when I multiply this negative u squared into u squared minus 1, I end up getting a negative u to the 4th plus u squared. And that's what I'm integrating with respect to u. So I end up with negative 1/5 u to the 5th plus 1/3 u to the 3rd plus c. Remember, u was cosecant. So this is negative 1/5 times the cosecant of x to the 5th power plus 1/3 times the cosecant of x to the 3rd power, and then plus c. So that's my final answer. So again, very, very similar to the way secants and tangents work, cosecants and cotangents work, although I have to remember that the derivative here includes this negative symbol. So I almost forgot that when I back substituted. Negative du, not du. So that's how we can integrate different like cosine times sines to different powers, secants times tangents to different powers, cosecants times cotangents to different powers. We can use U substitution along with playing around with these Pythagorean identities to make that work. So we can make all of these work. There are occasions on which I can't make them work. And on those occasions, sometimes I can use other tools. In particular, there are occasions on which we have trig functions, and there's other identities that would work better rather than the Pythagorean identities. So in the previous cases, I always had cotangent, cosecant to various powers, secant tangent to various powers, and those types of things. So the Pythagorean identities work kind of nice there. However, those aren't the only trig identities we have. And we can use any trig identities to manipulate a function and make it easier to integrate, put it into a more basic type of form. One such set of identities is what we call the product to sum identities. The product to sum identities are described here. If I take sine of A times sine of B, I get 1/2 times the quantity cosine of A minus B minus cosine of A plus B. And there are similar identities for cosine of A times cosine of, cosine of A times cosine of B and sine of A times cosine of B. This is really nice when we're multiplying sines with different arguments, or when we're multiplying a sine times a cosine with different arguments. Because I can easily integrate sine of a particular argument. Therefore, these product to sum identities are nice in a lot of situations. So we can use those in situations like this. Let's integrate cosine of 3x times cosine of 7x with respect to x. So this is cosine of an argument times cosine of a different argument. Therefore, I'm going to utilize this product to sum identity. Now, when I do this, I'm going to kind of rewrite this. I'm going to distribute the 1/2. So 1/2 cosine of A minus B plus 1/2 cosine of A plus B. That means I can take my original integration, my original integral, and I can rewrite that as 1/2 times cosine. Now, what would A minus B be in this case? It'd be 3x minus 7x, which is a minus 4x. And then plus 1/2 cosine of A plus B. Now, what would A plus B be in this case? That would be 3x plus 7x, which is 10x. And we're going to integrate that all with respect to x. Now, I don't have to do any substitution here. All I had to do is just rewrite this thing using the trig identity. And then each of these terms, I can use my basic rules of integration. The antiderivative of cosine is a positive sign. So we'd get sine of sine of negative 4x. And then I divide by negative 4. 1/2 divided by negative 4 is negative 1/8. So that's the antiderivative of that first term. And then I do the same thing here. Cosine of 10x, the antiderivative of cosine is sine. So we get sine of 10x. And then I would divide by 10. 1/2 divided by 10 is 1/20. And then, as always, I have to tack on a plus c. And that's it. That's the whole thing. Now, you may say, well, I know that sine is an even function, so I can factor out that negative symbol and it'll cancel out that negative. That's perfectly fine. You could have also, in this stage, said, actually, I called the 7x an a and a 3x the b, and so a minus b, you could have called a positive 4x. So you could have done that. You'd have gotten the same thing either way. So whether you use both negatives, you can write that down as negative 1/8 sine of negative 4x, or if you write it down as 1/8 times sine of 4x, both of those are perfectly fine. They're algebraically equivalent using the properties of the sine function. So while this thing wasn't easy to integrate, this thing is, and these two are equivalent via a trig identity. All right, so let's try another. Let's take sine of 10x times cosine of 4x and integrate that with respect to x. If you want, push pause on the video. I'll give you a couple seconds and then I'll do the problem. I don't expect anyone to memorize all these identities. There's lots and lots of trig identities. These product to sum identities that we're using now, you'd probably just go look up on either a trig identity sheet or look it up on the internet. But it's the sine cosine version. And therefore, it's going to be 1/2 sine of a minus b, where a is the argument inside of sine and b is the argument inside of cosine. So 1/2 sine of a minus b plus sine of a plus b. By the way, be careful on all of these positives, negatives. It's really easy to get one of these off. If you get one of those off, then the whole thing is going to be graded as incorrect. So I'm using this one. So now we're ready. Again, I'll distribute that 1/2. So we take 1/2 sine of a minus b. Now, again, the a is the argument inside of sine, so that's 10x, minus b, that's the argument inside of cosine, that's 4x. So 10x minus 4x is a positive 6x. Plus, again, distribute the half, you get 1/2 sine of a plus b. 10x plus 4x is 14x. and I want to integrate that with respect to x. Now I've split up one ugly looking term into two terms that are both individually easy to deal with. So I take the antiderivative of sine of 6x, that is negative cosine of 6x divided by 6. So we're going to get negative 1/12 times cosine of 6x. Again, antiderivative of sine is negative cosine. And then I do the same thing over here. Antiderivative of sine of 14x is going to be a negative cosine of 14x. And then I divide the coefficient by 14. 1/2 divided by 14 is 1/28. And then, as always, I just tack on a plus constant on the end. So that is how to use the product to sum identities to rewrite an expression into something that looks more in line with integrations that we've done before. Let's do another example of using trig identities. Here we have an integration of cosine squared 12x. Now, if you wanted to use a u substitution, it'd actually be pretty difficult in this situation. We couldn't use a u substitution. We couldn't let u be equal to cosine of 12x. Wouldn't work out very nicely. But what we can do is we can realize that cosine squared is just cosine times cosine. And therefore, it actually fits this. Cosine of 12x times another cosine of 12x is cosine squared of 12x. So we can use this product to sum identity with 12x as my A and 12x as my B. So that's what I'm going to do. Cosine squared, again, of 12x is cosine of 12x times cosine of 12x. I get 1/2 cosine. Now, when I take 12x minus 12x, I'm going to get 0. So I'm going to get 1/2 times cosine of 0. Plus, when I take 1/2 cosine of 12x plus 12x, that's 1/2 times cosine of 24x. Just so we're all on the same page, cosine of 0 is 1. It is not 0. Be careful about that. So this integration, let me actually write this integration again. This integration is 1/2 times 1 plus 1/2 cosine of 24x. When I take the antiderivative of 1/2, I get 1/2 times x, that is with respect to x, plus the antiderivative of cosine is going to be a positive sign. So I'm going to get sine of 24x, and then I'll have to divide the coefficient by 24. So that means my new coefficient is 1/48. So the integration of cosine squared of 12x becomes 1/2 x plus 1/48 sine of 24x. plus c. And again, if you actually found the derivative, it wouldn't look exactly like cosine squared, but it would be algebraically equivalent to that cosine squared of 12x. So there we go. Using these product to sum identities is pretty straightforward if we can easily add A and B and easily subtract the A and B. Usually I also distribute the 1/2. We saw, like in this case, when A and B were the same, then this number becomes a 1, and this thing in here became well, it was double my original angle. So you can rewrite these in a bunch of different ways, but they're pretty straightforward. Obviously, product to sum identities are not the only trig identities that we have. There are lots and lots of trig identities. And if you took a calculus course or a pre-calculus course, you probably have seen these other trig identities, lots and lots of trig identities. Ones that we're probably all very familiar with, like the reciprocal identities, which are things like secant is 1 over cosine, cosecant is 1 over sine. Tangent and cotangent are reciprocals of each other. We have quotient identities. We actually used one of these earlier, the fact that tangent is equal to sine over cosine, and cotangent is equal to cosine over sine. We used the Pythagorean identities earlier. We saw those. There's also the even-odd identities. That means that if you plug in a negative of the argument in for sine, you can pull that negative symbol outside. I referenced that earlier. And the same thing with cosine, but cosine is even. So cosine of a negative angle is equal to cosine of the positive of that angle. So negatives sort of die inside of cosines, but you can pull out a negative from the inside to the outside of sine. You can do the same thing. Tangent is also odd, meaning that's what it means to be able to pull that negative symbol out. So you can pull the negative symbol out in front of tangent if you want as well. There's some co-function identities. There's some difference identities. I won't go through all of these. There's double angle identities. One we kind of just saw. There's half angle identities. There's the product to sum identities that we just looked at. There's also sum to product identities that you could use as well. Now, in terms of integrating, usually sum to product makes things harder to integrate, but product to sum makes things easier to integrate. So some of these identities, in terms of integration, you're not going to use very often. In fact, on all of these, the ones that you're going to use really often, you should know quotients and reciprocals. You should be able to use the Pythagorean identities. You should be able to use the product to sum identities, but a lot of the other ones we won't use very often. However, just one use case of another identity, I'll look at in example 13. So example 13 asks us to integrate cosine squared of x minus sine squared of x. Now, that would cause me to have to integrate cosine squared. I could, I guess, do that using the product to sum identities. And then also integrate sine squared. Again, I could use the product to sum identities to do that as well. But it turns out cosine squared minus sine squared of x is actually equal to cosine of 2x through the double angle identities. So while I could have used product to sum and done sine squared, cosine squared separately, it turns out I can just take cosine squared minus sine squared is equal to 2x, cosine of 2x. Use that identity in order to integrate this thing. So let's go ahead and do that. Cosine squared minus sine squared, we could do in a more difficult way, but let's make it easier on ourselves. This is simply cosine of 2x using the double angle identity. And if we want to find the antiderivative of cosine of 2x, all we have to do is say that is sine of 2x divided by 2. So divide the coefficient by 2. So 1/2 sine of 2x plus c is the antiderivative of cosine squared minus sine squared of x. So some of these identities can be used to really quicken up our look for or our search for antiderivatives. Now, again, this is not a common one that I would ask in one of my classes. In my classes, the product of sum identities are going to be the most common outside of the use of the Pythagorean identities. So use substitution with Pythagorean identities is big, and the product of sum identities are also big in my classes. All right. So that is how to use trig identities and substitution to do a lot of different integration. Go back to the big, do a lot of integration with trig functions. Now, again, this was integrating where we were integrating functions that were involving trig functions. Later on, we'll do a reverse idea where we substitute in trig functions instead of substituting out trig functions. But that'll be in another section.